Hello and welcome to this video walkthrough on weight quantization using Jupyter Notebook. In this video, we will be exploring how to reduce the size of large language models using 8-bit quantization. We will be covering the code for absmax and zeropoint quantization, as well as generating text and calculating perplexity for both the original and quantized models. Additionally, we will be looking at how to load a pre-trained model in 8-bit format and comparing the dequantized weights to the original weights. So, let's get started. Hello and welcome to this video walkthrough on weight quantization using Jupyter Notebook. In this video, we will be exploring how to reduce the size of large language models using 8-bit quantization. In the current cell, we have an introduction to weight quantization. This technique is used to reduce the size of large language models, which can be quite large and difficult to work with. The introduction was created by @Maximelabon https://twitter.com/Maximelabon, and this notebook is a companion to the code from the following article, https://mlabon.github.io/blog/intro_weight_quantization/. In the next cell, we will be looking at some code for absmax quantization, which is one of the techniques we will be covering in this video. But for now, let's move on to the next cell and get started with the code. In this cell, we have some code for absmax quantization. This is one of the techniques we will be covering in this video. The purpose of this code is to quantize a tensor x using the absmax method. This method calculates a scale factor based on the maximum absolute value of x, and then scales and rounds the values of x accordingly. The code first calculates the scale factor by dividing 127 by the maximum absolute value of x. It then multiplies x by the scale factor and rounds the result to get the quantized tensor x_quant. To dequantize x_quant, the code divides it by the scale factor to get x_dequant. Overall, this code allows us to quantize and dequantize a tensor using the absmax method. In the next cell, we will be looking at some code for another quantization technique called zeropoint quantization. In this cell, we have some code for another quantization technique called zeropoint quantization. The purpose of this code is to quantize a tensor x using the zeropoint method. The code first calculates the value range of x, which is the difference between the maximum and minimum values of x. It then calculates the scale factor by dividing 255 by the value range. Next, the code calculates the zeropoint, which is the value that will be subtracted from the scaled and rounded values of x to ensure that they fit within the range of -128 to 127. The code then scales and rounds the values of x using the scale factor and zeropoint, and stores the result in x_quant. To dequantize x_quant, the code subtracts the zeropoint and divides by the scale factor to get x_dequant. Overall, this code allows us to quantize and dequantize a tensor using the zeropoint method. In the next cell, we will be installing some packages that we will need for the rest of the video. In this cell, we are installing necessary packages for the rest of the video. We are using the pip install command to install bits and bytes, accelerate, and transformers packages. These packages are essential for weight quantization using Jupyter Notebook. We can see the output of the installation process, which includes building wheels for accelerate and transformers. Once the installation is complete, we can move on to the next cell, where we will load the model in tokenizer and print the model size. In this cell, we are loading the necessary packages for weight quantization using Jupyter Notebook. We are using the transformers package to load a pre-trained language model and tokenizer. We then set the device to CPU and print the size of the loaded model in bytes using the get_memory_footprint function. As we can see from the output, we are also warned about not having an authentication token for the Hugging Face Hub, which is optional for accessing public models or datasets. In the next cell, we will extract the weights of the first layer of the model and quantize them using both absmax and zero-point quantization techniques. But for now, we have successfully loaded the necessary packages and printed the size of the model. In this cell, we are extracting the weights of the first layer of our pre-trained language model. We then use two different techniques to quantize these weights: absmax quantization and zero-point quantization. Absmax quantization calculates a scale factor based on the maximum absolute value of the tensor and scales and rounds the values accordingly. We can see the output of the absmax quantized weights, which are now represented as integers. Zero-point quantization calculates the value range of the tensor, a scale factor, and a zero point to ensure values fit within the range of -128 to 127. We can see the output of the zero-point quantized weights, which are also represented as integers. In the next cell, we will store the original weights, create models to quantize, and quantize all model weights using both absmax and zero-point techniques. But for now, we have successfully quantized the weights of the first layer using absmax and zero-point techniques. In this cell, we are storing the original weights of our pre-trained language model and creating two new models to quantize the weights using two different techniques, absmax and zero-point. We start by using the deepcopy function to create two new models that are identical to the original model. We then quantize the weights of each model using their respective techniques and store the quantized weights in two separate lists, weights_abs for absmax and weights_zp for zero-point. We use a for loop to iterate through each parameter in the model and quantize its weights using the absmax_quantize and zero-point_quantize functions. We also store the dequantized weights in the weights_abs and weights_zp lists. In the next cell, we will flatten the weight tensors and plot histograms to compare the original weights with the quantized weights. In this cell, we are comparing the original weights of our pre-trained language model with the weights that have been quantized using the absmax and zero-point techniques. First, we use the concatenate function to flatten the weight tensors of each model and store them in separate variables: weights for the original weights, weights_abs for absmax, and weights_zp for zero-point. Next, we use the matplotlib library to create two histograms for each technique, comparing the original weights with the quantized weights. The first histogram compares the original weights with the absmax weights, while the second histogram compares the original weights with the zero-point weights. We set the background style to ggplot and create a figure with two subplots using the subplots function. We then plot the histograms using the hist function, specifying the number of bins, alpha value, label, color, and range for each histogram. We add a grid to each subplot using the grid function and a legend using the legend function. We also add a title and axis labels using the set_title and set_labels/set_label functions. Finally, we improve the font size and layout using the RC and tight_layout functions and display the plot using the show function. In the next cell, we will generate text using the original and quantized models to compare their performance. In this cell, we have a function called generate_text that takes in a pre-trained language model, some input text, and a maximum length. The function encodes the input text using a tokenizer and generates new text using the pre-trained model. The generated text is then decoded using the same tokenizer and returned. We then use this function to generate text using the original pre-trained model, as well as models that have been quantized using the absmax and zero-point techniques. We print out the generated text for each model using the print function. In the next cell, we will calculate the perplexity of the generated text for each model. But for now, let's focus on understanding how the generate_text function works and how we use it to generate text with different models. In this cell, we have a function called calculate_perplexity that takes in a pre-trained language model and some input text, The function encodes the input text using a tokenizer and calculates the perplexity of the model on the input text. We then use this function to calculate the perplexity of the original pre-trained model, as well as models that have been quantized using the absmax and zeropoint techniques. We print out the perplexity for each model using the print function. The perplexity is a measure of how well the model predicts the input text. A lower perplexity indicates better performance. In this case, we can see that the original model has the lowest perplexity, followed by the absmax model and then the zeropoint model. In the next cell, we will see how to further reduce the size of the model by loading it in 8-bit format. But for now, let's focus on understanding how the calculate_perplexity function works and how we use it to compare the performance of different models. In this cell, we are creating a device object to specify whether we are using a GPU or CPU. Then, we are loading a pre-trained language model using the auto model for causal function from the transformers library. We are specifying that we want to load the model in 8-bit format to further reduce its size. Finally, we are printing the size of the model in bytes. That's it for this cell. In the next cell, we will be comparing the original weights of the pre-trained language model with the weights that have been quantized using the absmax and zeropoint techniques by flattening the weight tensors and plotting histograms. In this cell, we are comparing the original weights of the pre-trained language model with the weights that have been quantized using the absmax and zeropoint techniques. First, we are flattening the weight tensors of the original model and the quantized model. Then, we are plotting histograms to compare the distribution of weights between the two models. The blue histogram represents the original weights, while the red histogram represents the quantized weights. We are using 150 bins and a range of -2 to 2 for both histograms. We are also adding a grid, legend, title, and labels to the plot to make it more informative. Finally, we are displaying the plot using the plt.show function. That's it for this cell. In this cell, we are generating text using the quantized model. The generate_text function is used to generate text using the model_int8 and the input text I have a dream. We then print out the original text and the generated text using the print function. The original text is printed first, followed by a line of dashes, and then the generated text is printed. The generated text is from the LLM.int8 model, which is the quantized model. In the next cell, we will calculate the perplexity of the original model and the quantized model using the calculate_perplexity function. But for now, let's focus on the generated text and how it compares to the original text. In this cell, we are calculating the perplexity of the original pre-trained language model and the quantized model using the calculate_perplexity function. The perplexity is a measure of how well the model predicts the input text. We first print out the perplexity of the original model using the print function and the ppl.item method. We then calculate the perplexity of the quantized model_int8 using the calculate_perplexity function and print it out using the same method. The perplexity of the original model is 11.11, while the perplexity of the quantized model is 7.93. This means that the quantized model is better at predicting the input text than the original model. In the next cell, we will compare the perplexity of the original model and the quantized model in more detail using the calculate_perplexity function. In conclusion, we have successfully demonstrated how to use Jupyter Notebook to perform weight quantization on pre-trained language models using both absmax and zeropoint techniques. We have also compared the performance of the original pre-trained model with the quantized models using perplexity. The results show that the quantized models perform better than the original model. This technique can be useful in reducing the size of large language models, making them more efficient for deployment on resource-constrained devices. Thank you for watching this video walkthrough.